Students, hope all of you are well. So today I welcome all of you in the most important topic of this second unit lecture, that is the Gauss Divergence Theorem. So in this lecture, first of all, we are going to learn about the Gauss Divergence Theorem statement, try to understand it. Thereafter we will apply this into the problems. So let us start. So what is the statement of the Gauss Divergence Theorem says? It says that suppose we are having a volume V, which is a closed volume in a space whose boundary is a piecewise smooth oriented surface capital S. That is, if we are having in a space one volume that is bounded by a surface S. Now we consider a vector point function f of xyz be the vector point function, and this function must be continuous and having continuous first order partial derivatives in the same domain that containing the volume V, or say we can say that is a this containing the volume V. Then what we can get, one relation it will come, that is relation between the triple integration and the double integration. That is triple integration over the volume V of divergence of f dV. This is going to be double integration over S f dot n cap ds, f dot n cap ds. So from Gauss Divergence Theorem we can get the idea that divergence theorem converts one volume integration into a surface integration, where the left hand side of this integration gives us the volume integration and the right hand side integral is the surface integration. Now what is the meaning of this eta cap? Eta cap or n cap, this is basically the outward drawn unit normal through the surface. Okay, so let us try to understand it. Suppose this is a surface which is enclosed the volume V. So this region, basically this is the closed region inside this cylindrical type of structure, but not actually cylinder. This is an arbitrary shape of region that I have drawn here. So this volume is suppose enclosed by the surface S. This volume is enclosed by the surface S. This is the surface S, and eta cap is the outward drawn unit normal from each and every surface. So the divergence of f dV over this volume, divergence of f, that is going to be f dot n cap or eta cap ds. Okay, so in our exam what type of problem we are going to face? Basically it will come as the verification of the Gauss Divergence Theorem. So let us start the problem. So here the question is, verify the Gauss Divergence Theorem for a vector equals to x square minus yz I cap, y square minus xz j cap, z square minus xy k cap taken over a rectangular parallelepiped 0 less equals to a less equals to a, 0 less equals to y less equals to b, 0 less equals to z less equals to c. Okay, so here we are having a parallelepiped structure whose length is given from 0 to a, breadth will vary from 0 to b, and the height will vary from 0 to c. So now let us start the solution part. We have to verify the divergence theorem. So we have to write down the statement of the divergence theorem first before we start the problem. That is triple integration over V, divergence of f dV, this will be equals with double integration over S, f dot n cap ds or f dot eta cap ds. So let us first of all find out the left hand side part, that is the triple integration part. Now to calculate the divergence of f, what is the formula for divergence? In the video lecture second I have already told you how to calculate divergence and curl. So if you have not visited it, please visit it for your better understanding. So divergence of f can be calculated by del dot f. Del is the vector differential operator, and the formula for divergence of f is going to be del f1 del x plus del f2 del y plus del f3 del z. What is our f1, f2, f3? The components of I cap, j cap and k cap respectively. So del x will operate over x square minus yz, del y will operate over y square minus xz, and del z will operate over z square minus xy. So after this partial derivative, the result is coming as 2 into x plus y plus z. So we have to integrate this function 2 times of x plus y plus z over the volume V. So now the volume V can consist of the parallelepiped where the breadth, height and the width are vary from already I have told, length is varying from 0 to a, breadth will vary from 0 to b, and height will vary from 0 to c. So since here all the values of the limits are constant limit, so no matter with respect to which variable you want to perform the integration first. So first of all, we have performed the integration of this divergence of f with respect to x, thereafter followed by y, and then followed by z. So 2 times of x plus y plus z, 2 I have taken outside. Integration of x is x square by 2. Y and z are treated as constant while doing the integration with respect to x. So y integration with respect to x is going to be x into y. Z integration with respect to x, it will be x into z. Now limit of x we have to put, that is 0 to a. So wherever we see x is there, we have to put x equals to a. So in the next line we get the value, that is a square upon 2 plus a into y plus a into z. Now we have to do the same thing, integration with respect to y partially. So y will be the variable now, and rest of the things are be considered as constant. So a square by 2 dy, so it will be only a square by 2 into y. A into y, y integration is y square by 2. A into z, az will be treated as constant, so only y will come. So limit is 0 to b. We have to substitute the value, limit wherever we see y, we have to put y equals to b, and we get the result as a square b by 2 plus ab square by 2 plus abz dz. Now we have to perform the integration with respect to z. So it will come a square b by 2 into z, because this is fully constant term. Second term is also constant, ab square 2 upon z plus ab z square by 2. Now wherever we see z, we have to put c, and we can write it down in a simplified manner. So in the denominator everywhere the 2 is getting cancelled out, so the result will come as a into b into c into a plus b plus c. So this is the result of the triple integration or the volume integration. Now we have to perform the surface integration. So how to do this? This is the most important part of this problem. So to do the surface integration, first of all we have to draw the diagram of the space or the volume that is provided to us. So here it is the x-axis, here it is the y-axis, and here it is the z-axis. So along x-axis we will measure the length, along y we will measure the breadth, and along z we measure the height. Now the range of x is given from 0 to a, y is 0 to b, and z is 0 to c. So here is the parallelepiped, rectangular parallelepiped, over which we have to do the surface integration. So definitely from the diagram you can be able to see that 3 surfaces are in front and 3 surfaces are in back side. So therefore we are having total 6 surfaces. So over each and every surface we have to perform the surface integration. So before we do the surface integration, whatever the information we are having about the surfaces, we have to list down in a table form. So the table will be created like this. First you write down the surface, thereafter n cap or eta cap, thereafter ds, and some remarks about the surface. Okay, so now one by one we will think about the surfaces. So the first surface that we can see in front of us, that is the surface ABCD. Okay, so this is the surface ABCD. So if we shade this surface by these lines, then you will be able to see it more clearly. Okay, so this is the front surface we are having. So if you can see that this surface ABCD is parallel to YZ plane, because this surface has been shifted from the origin to x equals to a distance, and thereafter it is get fixed. So in the back side, which plane you can see the parallel to this ABCD surface, we are having YZ plane. So since it is parallel to YZ plane, so the outward drawn normal from this surface will be along the x-axis, outward drawn unit normal along the x-axis. So along x-axis, what is our unit vector? That is I cap. So we are having n cap equals to I cap. Since this surface is parallel to YZ plane, so here for this surface ABCD, basically y and z are varied, but x is fixed at a point A. So ds is going to be elementary area, that is dy into dz. And what are the remarks we are having for this surface? That is x is fixed at a distance A, while B will vary from 0 to B and Z will vary from 0 to C. If you see this A to B, then you can see the variation of Y, and A to D, that is the variation of Z. So Y will vary from 0 to B and Z will vary from 0 to C. So similarly, let us go to the back side of the surface ABCD. So just back side of the surface, we are having another surface, that is OEFG. So let us shade this surface by blue lines for your understanding. Okay, so this is the surface we are having on the back side of the surface, that is the surface OEFG. So for OEFG, blue color shaded surface that we are having, so this surface, from this surface, the outward run normal will be on the negative direction of x-axis. Okay, so outward run normal from surface to outside, the unit normal will be along the negative side of the x-axis. So in the negative side of x-axis, the unit vector is minus of I cap. So n cap is going to be minus I cap. Since this surface basically situated in YZ plane, therefore ds is going to be dy dz. Now for this surface, basically we have not traveled any distance, so this is strictly the YZ plane itself, in the YZ plane. So in YZ plane, the value of x equals to 0, but y will vary from 0 to b, that is O to E, and z will vary from 0 to c, that is O to G. Similarly, we are having the other surfaces BEFC. So what is about this surface BEFC? Let us try to understand it. So say this is the surface BEFC. This surface, that is the right hand side surface, which I am shading now with the yellow color. Okay, so this BEFC surface is parallel to which plane? This is parallel to XZ plane. So our ds is going to be dx dz. Now along this surface, since this surface is parallel to XZ plane, so perpendicular or unit normal of this surface will be along the y direction. Outward run unit normal will be in the y direction. So in the y direction, we are having the unit normal as j cap. So we have n cap equals to j cap. Now how we have fixed this surface, yellow color surface? We have traveled distance b along the y axis. So y equals to b. throughout the surface BEFC, where x will vary from 0 to a and z will vary from 0 to c. Now we go to the back side of this surface, that is AOGD. Same thing, it will be AOGD situated in xz plane, so our ds is going to be dx dz, where the outward run unit normal will be in the negative direction of y-axis. So in the negative direction of y-axis, the unit normal is going to be minus j cap. So it is going to be minus j cap here. And for this surface AOGD, y is exactly equals to 0, while x will vary from 0 to a, that is 0 to capital A distance, and z will vary from 0 to c, that is O to g. This height is nothing but 0 to c. So similarly we are having two more surfaces, that is the top surface and the bottom surface. So in the top surface we are having DCFG. So this surface is parallel to the xy plane. So the perpendicular or the unit outward run normal from this surface will be along the z direction. So in the z direction we are having the unit vector as k cap. Similarly, in the bottom surface AOEB or ABEO, the outward run unit normal in the opposite direction, that is in the negative side of the z axis. So the outward run unit normal is going to be minus k cap. Since both the surfaces ABEO and DCFG are parallel or situated in the xy plane, so our ds elementary area is going to be dx dy. Now for the surface DCFG, z equal to c, we have raised a height up to z equal to c, thereafter we have fixed it the surface. So z equals to c, while x will vary from 0 to a and y will vary from 0 to b. Now for the bottom surface AOBEO, we are having z equals to 0 because it is xy plane itself. X will vary from 0 to a and y will vary from 0 to b. So with all this information, one by one we are going to calculate the double integration. So one integration I have done fully, but you don't have to do all these steps. For your understanding I have done, you can skip some intermediate steps also, that I will tell you the shortcut way. So now we have to find out double integration over ABCD f dot n cap ds. So but what is the information we are having about ABCD? Just now I have told you, for the ABCD surface, n cap is going to be our I cap, ds is going to be dy dz, x equals to a, y will vary and z will vary. So all this information we have to put. So wherever we see x, we have to put x equal to a. Double integration will come with respect to y and z, limit of y and limit of z I have taken. Wherever we see x, we have substituted x by a, okay, and we have to take the dot product of this f vector with n cap or eta cap. So this n cap is nothing but our I cap. So I dot I is going to be 1. So from this we are getting y equals to 0 to b, z equal to 0 to c, only the first term a square minus yz dz dy. Z will vary from 0 to c, y will vary from 0 to b. So after this calculation, since it is a constant limit case, already many problems already we have done, so you can just see this step by step. You can calculate by yourself also. So after doing the all calculation, what we are getting, so the result is coming as a square cb minus b square c square upon 4. Now we have to do the surface integration for the back side of ABCD surface, just the parallel to ABCD surface. So that is going to be OEFG. For OEFG surface, x value is 0. So wherever x is there, we have substituted is as 0. n cap is our minus I cap, ds is our dy dz. From the table itself we have written this. So we have calculated this. Now it is coming yz dz dy. So if you notice, for the previous integration already we are having one part here, that is yz dz dy. So for yz dz dy we have calculated, and the result we are getting here, that is b square c square upon 4. This part, it is coming from the yz integration. Okay, so definitely this result is going to be b square c square by 4. You can do this step jump, no problem, if your calculations are correct. Now for the next one, similarly BEFC f dot eta cap. So for this surface, wherever we see y, we have to put it as b n cap equal to j vector, j cap. So j dot j is going to be 1, so only one term will be remaining from this all f dot eta cap, that is b square minus xz dz dx. After calculating, we get the result as b square ac minus a square c square upon 4. Similarly for AOGD surface, f dot n cap, it is just the opposite surface of BEFC, so y is going to be 0, so we get, and n cap is minus j cap, so the integration will come xz plus xz dz dx. Since here minus xz is there, but n cap is minus j cap, so this minus and minus will get absorbed, so we will get xz only, and the result definitely it will be a square c square by 4. How we can write down this? Because from this xz integration result is coming a square c square by 4, so same result it will come also, because we are having the same integration, only the minus sign we have to neglect here. And lastly, the two surfaces, there is a top surface and the bottom surface. Similarly we have done the integration for DCFG surface, z equal to c, n cap equal to k cap, so we get the integration of this part dy dx only. And similarly for ABEO, z equal to 0, so we get the value like this. So after adding all the surfaces, what is the final conclusion we get? That is ABC, A plus B plus C. So if you have noticed already, we have get this value in the left hand side term. So what we get, that LHS equals to RHS. Hence we can say that the Gauss divergence theorem is get verified. Now let us quickly come to summarize and make some short note about another problem of verify Gauss divergence theorem. Say we have having one function here, f vector, that is a vector valued function, vector point function, 4xz I cap minus y square j cap plus yz k cap, taken over a cube. So previous question is about parallelepiped, this question is about cube. Both the structures are exactly same, only for the previous question A, B, C are different lengths, but for cube all the lengths are going to be same only. So here the lengths have been given, x ranges from 0 to 1, y ranges from 0 to 1, z ranges from 0 to 1. So this problem is comparatively easier to calculate from in respect of the previous question. So before we start, we have to first find out the divergence of the f vector. So divergence of f vector, just we have told, that is del f1 del x plus del f2 del y del f3 del z. So del x of first component is our 4xz, del y of second component is minus of y square, and del z of the third component is yz, that you can see from the question itself. So the result will come after this doing the partial derivative, 4z minus y. So we have to do the triple integration of this quantity 4z minus y, where x will vary from 0 to 1, y will vary from 0 to 1, z will vary from 0 to 1, and dv is nothing but our elementary volume, which is nothing but dz dy dx. Okay, so we have calculated this triple integration. step by step I have done this. You can go through it and you can do by yourself and compare your result also for your verification, and result will come here as a 3/2 after the triple integration, because all the limits are constant, so integration is quite easy to solve. Now to perform the surface integration, we have to draw the domain and some table. So here this is the cube that we are having, all everywhere the length is going to be same everywhere. Now we are having again 6 surfaces. The front surface is ABCD, this surface. This is the surface we are having here, that is the surface ABCD. So for this surface, outward run unit normal will be along x axis. So along x axis we are having I cap, right, where ABCD is situated at 1 0 0, that is A is the code having coordinate 1 0 0. So x equals to 1, where y will vary from 0 to 1 and z will vary from 0 to 1. Now the backside of the surface ABCD is the surface OEFG, this surface OEFG, okay, this OEFG, this surface, backside surface. So for the backside surface, the outward run unit normal will be in the negative direction of x-axis, that is minus I cap. It is quite similar to the previous question. So as like that we have made the table. Similarly BEFC J cap, AOGD minus J cap, DCFG K cap, ABEO minus K cap. If you have understood the previous problem table, then this table is also quite same. Only the change is there. For the previous question, length is varying from 0 to a, that is x will get from 0 to a, y will get from 0 to b, z will get from 0 to c. But here all the results are going to be 0 to 1, 0 to 1 and 0 to 1. So as per that we have to make this table. Now let us come to one by one surface integration. So for first surface ABCD, f dot n cap ds, how to perform this? What are the information we are having? For ABCD surface, our n cap is nothing but I cap, our ds is nothing but dy dz, and everywhere we have to put x equal to 1 in f vector, and limit of y will be 0 to 1 and z will be 0 to 1. So after doing f dot n cap, only the first component will come, that is 4z. Okay, why? Because what is the term here? I can explain it little bit, because the first term is 4xz. So if I put x equal to 1, it will come 4z I cap. Now n cap is I cap, I dot I is 1, so you get 4z. Okay, so we have to integrate this 4z for the limit of y equal to 0 to 1, z equal to 0 to 1. So the result will come after the double integration as 2. Similarly for OEFG, f dot n cap is now minus I cap, and for this surface OEFG, x value is 0. So wherever we see x in f vector, we have to put x equal to 0, and ultimately the result will become 0 only after doing the dot product and putting x equal to 0. So result of this integration is 0. Similarly, we have calculated the integrations for the rest of the 4 surfaces, that is BEFC, result is going to be -1, AOGD, result is going to be 0, DEFG, result is going to be 1/2, ABEO, result is going to be 0. It is not going to be same result for every question, because for the function vector is given here, as per that only we are having these values. So these values are going to be changed if you are having different vector point function. So just keep this in your mind. So ultimately what will be the value of this surface integration? All these points we have to add, that is 2 minus 1 plus 1/2. So the result is going to be 3/2. Okay, so here we can declare that here also LHS equals to RHS. So the the Gauss Divergence Theorem is get verified. Okay, hope you have understood this. Thank you all.